AI systems don't only fail at the model. They can be misled through poisoned documents, leaky embeddings, tampered artifacts, and hostile inputs. In this topic, we'll focus on protecting trust across the full RAG and model lifecycle. So far, we've built the outer defenses: identity, secrets, secure development, supply chain, and prompt safety. Now we move inward to the things the AI system trusts directly: its knowledge sources, embeddings, and model artifacts. If integrity fails there, the rest of the system can be undermined. RAG changes the security problem because the model is no longer the only trusted component. Documents are ingested, parsed, chunked, embedded, stored, retrieved, ranked, and injected into the prompt. A weakness at any step can shape the answer. Poisoned documents, tampered embeddings, loose permissions, or manipulated retrieval can all become model instructions in practice. Protection has to be layered: validate content, enforce access, constrain retrieval, monitor outputs, and treat retrieved context as high-impact input. RAG poisoning starts before the model ever answers a question. An attacker gets content into a trusted ingestion path, such as an upload, crawl, email, PDF, or support ticket. That content may include false facts, hidden text, metadata, or prompt injection instructions. Once indexed, retrieval gives it authority. The model may repeat misinformation, recommend unsafe steps, expose data, or bypass policy. The key control is source risk classification and sanitization before anything becomes retrievable. Source ingestion should be a risk decision, not a copy operation. A signed internal policy may be high trust, while a public crawl or user upload needs stronger checks. Score each source for ownership, authentication, freshness, reliability, sensitivity, and review status. Then validate the content for malware, prompt injection, hidden text, unsafe links, encoding tricks, and policy issues. Based on that result, content can be accepted, reviewed, quarantined, restricted, excluded, or discarded with an audit trail. Metadata is not just bookkeeping. In retrieval systems, it becomes part of the access control path. If a request can supply fields like tenant, role, category, date, location, or sensitivity, an attacker may reshape what the retriever sees. That can surface restricted documents, bury poisoned ones, or make malicious content rank higher. Treat metadata as untrusted input. Derive critical filters from authenticated server-side claims, validate allowed values, enforce authorization before ranking, and log enough detail to investigate abuse. In access-aware RAG, authorization has to travel with the query. The user's identity, role, attributes, policy rules, and tenant context become filters that shape retrieval. Ideally, those filters run before similarity search, so restricted chunks never become candidates. Post-filtering can help, but it should be a fallback, not the main control. For multi-tenant systems, isolate indexes or namespaces. Then test with realistic questions, because indirect retrieval can expose data that direct access checks miss. An embedding is like a semantic fingerprint. It is not readable text, but it can still point back to what the data is about. Nearby vectors may reveal customer concerns, medical issues, legal matters, product plans, or incidents. Search can also expose whether a sensitive concept exists at all. More advanced attacks may infer membership or partial content. Protect embeddings like sensitive data. Classify them, restrict access, monitor use, and apply retention rules. Vector databases need isolation because similarity search can reveal relationships, not just records. Separate tenants, environments, and sensitivity levels with namespaces, collections, or dedicated indexes when risk is higher. Apply least privilege to every operation: upsert, query, delete, export, and metadata changes. The biggest concern is silent harvesting, where repeated nearest neighbor searches or bulk exports reconstruct sensitive context. Monitor query patterns, enforce boundaries, and treat vector access like production data access. Encryption for vector systems has to cover the whole data path, not just the database. Use TLS, private networking, and strong service authentication for connections. At rest, encrypt embeddings, metadata, indexes, snapshots, and backups. For higher risk data, use envelope encryption and separate keys by tenant, environment, or sensitivity level. Pair encryption with identity controls, audit logs, export limits, and secure backup retention, because encrypted data can still be exposed through weak operations. Model artifacts are critical supply chain assets. Risk can enter at the source during fine-tuning, through adapters, tokenizers, configuration files, or dependencies, and then travel all the way into deployment. The result may be a backdoor, data leakage, unsafe behavior, or unreliable outputs. Integrity control means proving provenance, reviewing training data lineage, validating evaluations, and securing the registry and deployment path before the model is trusted in production. Every model release should be handled like a software supply chain artifact. Package the weights, tokenizer, configuration, adapters, and runtime files. Generate checksums and sign the package, so deployment systems can verify both integrity and publisher identity. The approved registry becomes the source of truth for version, lineage, review status, and policy. CCD should verify everything before deployment and fail closed if anything is unsigned, unapproved, stale, or mismatched. Deployment is not the finish line for integrity. Each time the service starts, verify that the running artifact matches the approved hash and signature, and that configuration, tokenizer, dependencies, and registry metadata have not drifted. Keep watching behavior as well. Refusal rates, tool calls, output patterns, and policy violations can reveal tampering or unexpected changes. When a mismatch appears, alert quickly and roll back to a known good model, configuration, or retrieval index. Adversarial input testing means treating every input path as potentially hostile, not just the chat prompt. For RAG systems, that includes retrieval queries, documents, JSON payloads, files, images, and API calls. Tests should look for prompt injection, jailbreaks, schema abuse, hidden instructions, malware links, and attempts to extract data. The important practice is automation. Run these cases in CI/CD, then repeat them whenever models, prompts, indexes, or policies change. Trustworthy AI depends on trustworthy inputs, protected retrieval paths, and verified artifacts. Secure RAG by validating sources and filtering access. Treat embeddings as sensitive, with encryption, monitoring, and least privilege. Validate models through provenance, signing, testing, and tamper detection. Next, we extend these controls to APIs and data protection.